Welcome to this presentation on Wright stuff and ping pong parachute. Perhaps you've already done Science Olympiad or you've attended the previous workshops to know a couple of things, but otherwise, this is, so I'm assuming you've watched the first presentation on the general build events because I'll be building on from there. I wanted to remind you what the cool stuff you can do with aerospace engineering. So you might have heard bad things about Wright stuff or ping pong parachute. Maybe because it's kind of like you have to buy a kit and that sucks, or you have to do so much practice, but the gym's always closed. Well, that's the bitter truth of these events. But really, these events are fun if you put the time and effort into them. So these events will help you get started on a path towards aerospace engineering, and you can do all sorts of things with these basic knowledge. You can design. And essentially, this will help with your future academic pursuits if in this field of study, and we'll make sure that what you learn is grounded in some sort of physical reality. And so the two events that we have going for us are somewhat representative of aerospace engineering. There's rockets and parachutes, and also airplanes. So we're going to talk about these two kind of aspects with Wright stuff and ping pong parachute. So Wright stuff is an event in which you build a plane, usually out of balsa wood, because it has to be light, and it's powered by a twisted rubber band. This twisted rubber band is called a motor. So you can bring up to 2 planes, a couple calculators, tools, and the flight logs to the competition. Then you launch your plane, and they will record how long it stays in the air, with the objective of making sure it stays in the air the longest amount of time. Now, these planes are defined by several constraints, and if you do not meet these constraints, you will be ranked last. So it's like not as bad as being disqualified, but you must follow these constraints. You are allowed to use essentially any material except for boron filaments, and a boron filament is a type of a very elastic and strong material. So it's essential that it's mostly for the motor that you'll be using it. And the reason why is that boron is toxic, so they want to avoid toxic things and just ensure safety. The plane, the next point on the list, the plane must weigh at least 8 grams. So I guess that's some sort of working constraint there. Ideally you want to minimize the weight of the plane, but they've set some sort of minimum that you can't go below. And similarly, they have defined a maximum limit on the length of the wingspans. So an airplane, like you can see on this picture here, consists of a front wing called, I guess we can call it the main wing, and the stabilizer in the back. So this main wing can have a wingspan of 45 centimeters and a chord of 9 centimeters or less. And wingspan is when you look at the plane from the top, it's going to be the distance from the 2 edges of the wings that is perpendicular to the fuselage or the body of the airplane. And the chord is the distance between the leading edge of the wing and the trailing edge of the wing. And so you can consult this picture here. And there's similar dimensions for the stabilizer. Now, what's the stabilizer? It's actually, I guess, it consists of a small wing, a little rudder, or this little tip that points vertically, and they're called horizontal and vertical stabilizer. So I'll show you the purpose of why these are necessary, but what you need to know is that this horizontal stabilizer can be no more than I think 28 centimeters and 24 centimeters, 7 centimeters long. Okay, anyways, the propeller has to be no more than 24 centimeters. Why? Because the bigger the propeller, the more powerful the airplane. So they have some sort of limit to make sure it's not too powerful. And similarly, the rubber band. The rubber band, usually the thicker the band, the stronger you can twist it before it rips. So that's why they set a maximum limit of 1.5 grams. And so you're allowed to bring 6 of these rubber bands in case one breaks. So that's fine. Now, I guess if you've seen this picture on the previous the introductory build event workshop. So the way this airplane is powered, I'll remind you, is that you take a rubber band and you twist it. If you twist it, it will experience torsional stress and it will want to release it. So when you twist the rubber band, you hook one end to the motor, which is free to rotate around this bearing right here. But the other end, you hook onto a stationary hook, which cannot move. So you'll have rotation with respect to this hook of the rubber band. That will twist the motor and propel the aircraft forward as the propeller pushes air back. So there's quite a lot of stuff going on. I mean, this picture is quite an oversimplification, but just take a look. I mean, this little blue region with the propeller, the thrust bearing, the hanger or tube, and the motor hook, looks like a lot of little small details. Are you sure you can make this yourself? And if you are sure, well, how about the propeller? Are you going to make that yourself too? Or are you going to buy it? So in fact, what materials would you think you'd need? So obviously we can't make we can't opt for a metal propeller. I mean, even though it's durable, it will be too heavy. And maybe even wood is too heavy of a material to use for the main fuselage. So you run into all sorts of issues when if you want to start designing this from scratch. But fortunately, I guess this problem has been solved before. And what people who have done this before recommend is starting with a kit. It's I've shown you this previously. This is a picture of what comes inside a Freedom Flight kit for Wright stuff. They have designed an airplane that meets SILE rules, and they have enough material to build 2 complete airplanes. And they've really put some thought into the material choices. So they've made carbon fiber rods. They have mylar sheets for the wings. Essentially, mylar is like a plastic foil. So it's like a plastic shopping bag material, but with aluminum foil coating on one side. So that's what mylar is. It's lightweight and strong. So we can't really make that from scratch. And they've put some thought into how you can adjust this airplane, because if you build it somehow, it might be that you've applied too much glue somewhere and you need to shift something. So they've put some thought into how you can adjust and slide things around to optimize the performance. And to help you build it, they've included the instructions for assembling it. And along with these instructions, they have lots of pictures and lessons in aerodynamics. So if you want to learn this field, or if you want to learn this subject, and do so in a kind of a practical way, this is the place to go, or the thing to do. Now, once this kit costs about $70, but I recommend that you start with a kit. After you've built maybe 1 or 2 of these airplanes, and you feel confident that you know what you're doing, you can try making one on your own. And there are plans that you can use online. You can try making your own plan for the airplane, like what length to cut sticks, what shape to make the propeller. But a couple of useful things that I found was you might want to look at where people get rubber bands. So on the SILE forum, they recommend a couple of websites where you can get these rubber band motors. And one interesting thing is that rubber tends to deteriorate with age. So if you, for example, take a rubber plastic glove and you put it in the sun for maybe a month or 2 or 3, or keep it hot, it will start crumbling apart. So to make sure that your rubber band doesn't crumble apart at the competition or doesn't get weaker as you stress it continuously, I recommend that you swap out these rubber band motors every month so that your performance is consistent. In terms of, so the way you would wind a rubber band is, I showed you this, I guess, this gesture of twisting up rubber with your hands. But if you accidentally drop it, you'll have to start all over again, and it's not really convenient. So there is a special mechanism that people use. As you see here, there's a white handle which you use to turn the thing, and the hook, metallic hook. So you latch the rubber band on through this hook here, the motor hook, and the other end you loop over the hook on the winding mechanism, and you turn the white handle many times, maybe like several hundred or maybe up to 1,000 times, and then you remove the rubber band from this hook and you latch it onto the rear motor hook. So that's the procedure. If this doesn't make sense, it will make sense once you get the parts. But keep in mind that you would also need to buy this thing. It costs about $15, so it's not that much, but it saves a bunch of time. And if you're interested in propellers, the one brand that many people on Siley recommend is Ikara. And I guess we can, like, if you click on this link, then you can get to their webpage and look at stuff. So yeah. Now, once you build the kit, you'll need lots of patience to build this kit because it's quite a lot. You have to wait for glue to dry. There are a lot of little things that you need to make sure are made just right. So once you've spent a lot of time building this kit, you'll need to spend even more time testing it. And this is how you beat the crowd, because everyone buys the kit essentially, or so many people do, except someone bought it the night before competition. So they're not going to really know how to get good performance out of this device. But you, if you start like maybe 2 or 3 months in advance and practice a lot, you can make lots of modifications and understand how each of these kind of three chief parameters I have here affect the flight patterns of the airplane. So let's start with here. You'll notice that the wing, which is here, is attached to the fuselage or the main body of the airplane at 2 points. Those are sliding joints. So there's a bit of friction, but you can move this around forwards and backwards. That's important because by moving the wing, you're moving where the center of lift is and where the center of gravity is. So you're kind of adjusting the forces or the position of where the forces are that are supposed to balance out on the airplane. So by moving around the wing, you adjust the center of lift and center of gravity. And it's important that you have all of these forces kind of balanced out. You don't have too much of these forces on one side, or else the airplane could tip over. So the next moment we want to talk about is the wing. And really the design of the cross-section of the wing or the aerofoil affects how much airlift and drag you'll have. And engineers spend a lot of time making better and improving these designs. But the basic shape is kind of like a stretched out teardrop shape or an aerofoil that has its own special name. So if by varying the length of this aerofoil, its cross section and the angle at which it's inclined, so you can tilt your wing, you can have your wings be horizontal or tilted up. That's the angle of attack here. So by adjusting this, you can optimize or control how much lift force your wings are producing. And so that's useful. And finally, you want the back here, you have this stabilizer. And this is basically another wing with a rudder. Now, a rudder is used to steer objects flowing through, traveling through fluids. So if you've ever been kayaking or you've looked at boats or you know what a rudder is anyways, what a rudder does is, let's say you're looking at the boat from into the camera, and you're looking at the front of the boat. In the back, there's a rudder, which can either flap to the side or to the other side, or remain in a neutral position. If you flap the rudder to this side and the boat is moving forward, the water pushes against this rudder. It's kind of like a barrier. So as it pushes, since this rudder has some sort of distance from the main body, there will be a torque that wants to rotate the boat this way. So if you flap the rudder this way, your boat will turn this way. And if you flap the rudder the other way, your boat will turn the other way. So why do you need to have a rudder? It's because your airplane isn't going to fly in a straight line. You're constrained to a gym, which we can imagine it to be like a rectangle. So that means to maximize flight time, your airplane has to fly in circles. And by controlling the angle at which you turn the rudder, you control the radius of curvature that you fly. And it's important to optimize this because airplanes aren't good at flying in small little circles. They waste a lot of energy turning. But you can't have them fly in too big of a circle because then you'll bump into the wall. So you need to control the rudder angles. And another interesting note is that the stabilizer, as we've seen in this picture, it's designed to push down on the airplane. And that is important because you are supposed to stabilize all of the forces and the moments acting on this airplane. So if you've seen how levers work, essentially, you can imagine this airplane. It's like a lever with the fulcrum at the center of gravity. And there's a center of lift, which is the force that the wings produce, and it acts here. But looking at this picture, if there were no stabilizer, the center of lift would cause the airplane to kind of tilt down because it's pulling it up behind the center of gravity. So that's why you need a stabilizer to push it back down and keep the airplane level. And if you don't have a balance between the stabilizer's force and the center of lift, or the lift force, what could happen is that your airplane could fly up, or like as you launch it, your airplane would fly up, but it will fly so high up that it can't generate enough lift force, so it will kind of fall down. And I've seen this happen so many times that you launch the airplane, it goes really steep up and then it falls, and then really steep up and falls, and it keeps doing that. And it's wasting a lot of energy in climbing the air instead of just traveling forward. And the energy comes because it's kind of trying to increase its potential gravitational energy instead of overcoming frictional losses. So that's that. You need to, that's why it's important to optimize things. If you just build this thing and hope it works, it won't. So my next topic would be how to help you approach this problem systematically. Because if you just start changing things around and hoping it works or kind of guesstimating it, you'll lose track of the adjustments you've made. So that's why this event requires you to bring a prep or a flight log. And you might think this is an extra bit of work, but this is actually a blessing in disguise. The point of these flight logs is to help you collect the data that you'll need to improve your design. And you can't really store all of this in your head, really. So the Science Olympiad competition requires 3 parameters. It's the length of the motor, or of the rubber band before you wind it up, the number of turns on this motor, and the time that your airplane has been flying. Now, there are additional 3 more parameters that you are required to include, but you're free to choose which ones. And one of the examples they gave was the estimated maximum height, which, if you know your airplane is supposed to fly in loops, it's how high it goes on the spiral before it starts descending. Another one is the torque of the motor at landing, or the number of turns that was left in the motor. So essentially what this means is if your airplane was flying and flying, and then it crashed, and you lift the motor up when you walk to it, and it turns out that the motor was actually still twisted, and you lift it up and the propeller starts spinning. Well, what this means is that if your airplane didn't crash for whatever reason, it could have continued to fly. So that means you didn't utilize the full potential of the motor. So I guess they want you to see, they want you to try recording that. And another one that I recommend is the turn radius and the rudder angle. So by adjusting, remember, the rudder angle here, you can control the radius at which the airplane turns. And this is, so that's how you'll know. If you arrive to the competition, the event supervisors will let you know what the height of the room is and what its approximate dimensions are, so that you can make the adjustments. And these are important because if you've been practicing in a room that has a huge ceiling, and then the competition is held in a room with a really low ceiling, you need to be able to make some adjustments, because the way you've been practicing, if you launch it, it will crash into the ceiling. And if that happens, then it will fall down and it will go down from there. So just to summarize, the goal of this event, this entire event, Wright stuff, is not just to build a model airplane, but it's also to practice making adjustments and learning how these adjustments will increase and optimize flight time. So to recap what parameters you can change, I've made this little table here. Now, obviously, you want to minimize the weight. The weight is something we can control. If it's super heavy, it will want to fall down. The airplane, the propeller will have to spend a lot of energy pushing the mass or pulling the mass forward. So that's not good. Minimize the weight. However, we want to maximize the wingspan, and both for the main wing and maybe the stabilizer, because that's what produces the lift force. So the more lift we have, the I guess the longer you can fly. And that's something we want to maximize. So now in between, we can't really, there are several parameters which we don't know if we want to make this a lot more or a lot less. It's really something in between, in the middle. So the angle at which you turn the rudder and the stabilizer angles and the wing angles, as well as the position of the wing along the fuselage. Remember this red circle here, where do you have this wing attached? That's something for you to play around with and determine what is that works best, because there's really no formula. It's really complicated to predict, and in fact, aerospace engineers, they use a thing called finite element modeling. So they use computers to solve this because there's no pen and paper formula that can tell you where to put these things. It's not complicated. So that's why they're recommending you the next best thing, because which is trial and error. We don't have access to computers to find the optimum. In reality, you'll be using those, but here, since it's just a model airplane, you'll have to do things by your hands. So once again, without all of this effort that you invest in optimizing your design, you really won't be better than your competition. You might get lucky, or you might not get lucky. It depends. So that's why it's important to optimize and spend a lot of time. All of the people on these forums, all the adults that are coaching this, that's what they say. This event is about testing, not building. So I guess that's the kind of the important stuff I wanted to say. I wanted to motivate you, or just show you something awesome that I found while I was preparing for this presentation. So I want to show you a video of people building human-powered aircraft. So what you do is you put a person inside of this pod, and there are two pedals, and the person pushes them like you would a bike, and that turns a chain and transmission, and that drives the propeller here. So you can literally fly, except you have to sit in a contraption. But there's no motor, you have to push the wheels yourself. And yeah, so people make pretty awesome things in their spare time, just like you could if you do this event. Anyways, so this, if you want to learn more, this thing is called the International Bourbon Rally. I think it's mostly done in Japan, but these things have been going on since like the 30s, the 70s, basically. So anyways, I hope you enjoy. I'll grab a drink of water while you watch this video. So those people I think are the ones who built the device. I think it yeah, I click turn here, and you notice how as it's turned, it's kind of going here because this thing is going to calculate, so it will need to kind so that was that. I think what happened is the wind pushed on the boat or on the flying craft, and caused it to turn. And as it turned, it tilted. And once its wing touched the water, then, well, it all went down from there. So I hope this kind of was exciting. And these people do this in their spare time, and they're university students. So they're like even more busy than you are with coursework and stuff like that. So final comments. So I gave you a presentation on a very surface level presentation on what to expect from this event and how to approach it. But this is really not all of the wisdom that exists and that you should try to seek. I recommend that I will send this presentation out later and click on these two links. These people are seasoned aerospace engineers and coaches for this event, and they've kind of put a lot of their own wisdom into what this event is about, and people have found it useful. So check that out. If you want to, so the website that sells the kits is called Freedom Flight Models. So I guess I have not been sponsored by them, but please click them. I guess that's the only one I know of. So if you don't want to spend a bunch of time looking for it, then you can try this one right away. Now, this event, it's not only rich in practice, it's also rich in theory if you seek it. So if you want to learn more about aerodynamics, there are plenty of websites that kind of teach it to you. Also, there are textbooks. If you want to start with aerodynamics, you can try doing chapters, I think 14 or 13, I think, of the Giancolli textbook. Basically, somewhere in the middle, they talk about fluids. And finally, if you want to try building your own, there are people who make their own model airplanes. One of the places are, it's a website called Hip Pocket Aeronautics or whatever that I found. And what they have is basically, you can print out or download a PDF of a page, and it will tell you what shapes and sizes to cut out of wood to make the airplane. So you can imagine it's like if you feed this to a laser cutter, it will cut out all the shapes for you, except you're the laser cutter and you have to cut them out. So yeah,